Imagine having two magical coins. You flip one coin in New York, and the instant it lands on heads, the other coin in Tokyo somehow lands on tails at exactly the same moment, even though no one touched it. It sounds impossible. It sounds like science fiction, but something surprisingly similar actually exists in nature. It's called quantum entanglement, and it's one of the weirdest discoveries ever made in physics. In fact, even Albert Einstein hated the idea so much that he called it spooky action at a distance. So what exactly is quantum entanglement? How does it work? And does it really mean information can travel faster than light? Let's break it down as simply as possible. First, we need to zoom into the tiniest building blocks of the universe. Everything around you, your phone, your body, the air, even distant stars, is made of tiny particles like electrons, photons, and atoms. But these particles don't behave like everyday objects. Instead of acting like tiny balls, they behave according to the strange rules of quantum mechanics. One of those strange rules is that a particle doesn't always have one definite state. Imagine a spinning coin. While it's spinning, you don't know whether it will land on heads or tails. A quantum particle is even stranger. Before you measure it, it behaves as if it's in multiple possible states at the same time. Scientists call this a superposition. Only when you measure the particle does it appear to choose one specific state. Now here's where things become truly bizarre. Sometimes two particles are created in such a way that they become connected. Not physically connected by a wire, not connected by gravity, but connected through their quantum properties. These particles become entangled. Think of them as two dancers performing the same routine. Even if you separate the dancers and place them on opposite sides of the planet, their performance still remains linked. If one particle is measured and found to have one property, the other particle instantly has the corresponding property, even if it's incredibly far away. Imagine you have two magical gloves. One is packed into a box and shipped to London. The other is shipped to Sydney. When someone opens the London box and discovers it's the left glove, they instantly know the Sydney box contains the right glove. That doesn't seem mysterious because the gloves already had their identities from the beginning. Quantum entanglement is different. The particles don't seem to have definite identities before they're measured. It's as if reality itself waits until the measurement happens, and when one particle is measured, the other instantly becomes linked to that result. This isn't just an idea. Scientists have tested quantum entanglement in laboratories for decades. They've created entangled photons and separated them by kilometers. They've even sent entangled particles between satellites and Earth. Every experiment keeps confirming the same strange behavior. The particles remain correlated in ways that ordinary physics cannot explain. So does this mean information is traveling faster than light? Not exactly. This is one of the biggest misconceptions. Although the measurement outcomes appear instantly connected, you can't use entanglement to send messages. Imagine trying to send Morse code using random coin flips. Every flip is completely unpredictable. Even though two entangled particles are connected, each individual measurement is still random. You can't decide whether your particle becomes heads or tails. Because you have no control over the outcome, you can't use it to send useful information. That means Einstein's theory of relativity is still safe. Nothing carrying usable information has been shown to travel faster than light. So why did Einstein dislike quantum entanglement? Einstein believed that the universe should have clear, predictable rules underneath everything. He thought particles must already possess hidden properties before we measure them. In 1935, he and two other physicists proposed a famous thought experiment known as the EPR paradox. Their goal was actually to show that quantum mechanics had to be incomplete. But decades later, another physicist named John Bell developed a mathematical test called Bell's theorem. Scientists performed experiments based on Bell's work. The results consistently supported quantum mechanics, not Einstein's hidden variable explanation. It was one of the greatest surprises in modern science. Even today, physicists continue performing more precise experiments, and quantum mechanics keeps passing every test. So if entanglement isn't useful for faster-than-light communication, why is everyone so excited about it? Because it could revolutionize technology. One of the biggest applications is quantum computing. Today's computers store information using bits. Each bit is either a 0 or a 1. Quantum computers use quantum bits or qubits. Because qubits can exist in superpositions and become entangled with one another, they can process certain types of problems far more efficiently than ordinary computers. This doesn't mean quantum computers are faster at everything, but for specific tasks, like simulating molecules, optimizing complex systems, or breaking certain encryption methods, they could be dramatically more powerful. Entanglement is also making communication more secure. Scientists are developing quantum communication systems where any attempt to intercept the message changes the quantum state. This means eavesdropping becomes detectable. Several countries have already demonstrated experimental quantum communication networks, and researchers are working toward a future quantum internet. A quantum internet wouldn't simply be a faster version of today's internet. Instead, it would allow quantum devices to share entangled states over long distances, opening entirely new possibilities for computing and secure communication. The strange world of entanglement also raises deep philosophical questions. Does reality exist independently of observation? Why do measurements seem to matter so much? Are particles somehow connected outside our normal understanding of space and time? Physicists still debate these questions. Some interpretations suggest the wave function collapses during measurement. Others propose that every possible outcome happens in separate branches of reality. Some researchers even wonder whether space and time themselves emerge from deeper quantum relationships. The truth is, no one fully knows. That's what makes quantum mechanics so fascinating. It's one of the most successful scientific theories ever created. Its predictions have been tested with incredible accuracy. Without quantum mechanics, we wouldn't have lasers, MRI machines, semiconductors, smartphones, or much of modern technology. Yet despite all its success, nobody completely agrees on what it truly means. As the famous physicist Richard Feynman once joked, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And perhaps that's the beauty of science. Sometimes discovering how nature behaves is easier than explaining why it behaves that way. Quantum entanglement reminds us that the universe is stranger than our everyday intuition. Two tiny particles can become linked in ways that seem impossible. Not because they're secretly sending messages across space, but because the quantum world follows rules completely different from the ones we're used to. The more scientists study entanglement, the more they uncover technologies that could transform computing, communication, and our understanding of reality itself.